Right, let's dive straight into this. If you spend any amount of time driving on the highway, you know exactly what I'm about to talk about. It's that relentless, vibrating hum that just seems to seep right through the floorboards of your car. Well, today, in this explainer, we are looking at a literal game changer in acoustic engineering. Engineers are actually using these brilliant little honeycomb structures to hack the physics of sound and stop road noise completely dead in its tracks. So here's the roadmap for today. We're going to start with the roar of the road, look at why traditional foam falls short, and then introduce the acoustic metasurface. After that, we'll get into the magic of anti-resonance, check out the journey from lab tests to highway drives, and finally, look at a much quieter future.
Okay, part 1. The roar of the road and understanding TPN. Why, with all our modern engineering, are cars still so incredibly loud?
I want you to imagine you are cruising down the highway in a brand new electric vehicle. The old, noisy internal combustion engine? Gone. The electric motor is practically silent, and the aerodynamics are super sleek. Yet, the second you hit 70 miles per hour, the cabin is just roaring. So, why? What in the world is generating all that noise when the engine isn't making a single sound?
Well, the primary culprit is something called tire-pavement interaction noise, or TPIN. Research shows that once you hit about 70 to 80 kilometers per hour, the friction between your tires and the pavement completely takes over as the dominant noise inside the cabin. Here's what's physically happening down there. Inside your tire, you have a toroidal cavity, basically a giant rubber donut, filled with compressed air. When the tire smacks against the pavement, it creates these structural vibrations that agitate the compressed air inside. That generates a relentless, low-frequency hum that shoots straight through the wheel, up the axle, and right into your seat.
Moving on to part 2, why foam falls short. Let's talk about how the industry has been trying to fix this, and honestly, coming up pretty short.
For a long time, the standard Band-Aid solution for tire manufacturers has been pretty low-tech. Just glue a thick ring of polyurethane foam right around the inside of the tire. The idea is that this porous foam will absorb the sound, but it really doesn't work well. You see, foam basically converts a tiny fraction of sound wave energy into heat. But at these specific low frequencies, the sound waves are massively larger than the tiny little pores in the foam. It's kind of like trying to stop a flood with a kitchen sponge. The foam only catches a very narrow sliver of the noise, letting the rest of that rumbling energy pass right on through, all while adding totally unnecessary weight to the wheel.
Which brings us to part 3. Enter the acoustic metasurface. We desperately needed a better way to block this noise without just stuffing heavy foam everywhere.
Now, what is really fascinating here is the geometry itself. We aren't looking at some thick, dense slab of material. It's actually a super lightweight, carefully engineered 3D aramid honeycomb core, which is topped with a remarkably thin silicone rubber plate. This is an artificially designed material, what engineers call a metasurface. It's incredibly thin, literally a sub-wavelength thickness, but it's specifically built to manipulate the actual phase and direction of sound waves.
Let's break down why this design is so incredibly clever. The engineers chose hexagonal unit cells because structurally, hexagons don't warp or deform when you bend them around the curved inner surface of a tire rim. They hold their shape perfectly. This rigid honeycomb core is then capped with a highly flexible, low-viscosity silicone rubber that has the genuinely awesome name of dragon skin. This whole setup is bonded in just a 3.5-inch strip right around the inner rim of the wheel. And here is the real kicker. Because it sits on the rim, it requires absolutely zero changes to the actual heavy rubber tire itself. No change to the mechanical strength, no change to the tread. The whole problem is solved right at the rim.
Section 4. The magic of anti-resonance. This is honestly the most mind-bending part of the whole explainer. This thing basically acts like an acoustic force field.
Okay, stick with me here. Please don't let the dense physics jargon scare you off. The term is negative effective dynamic mass density. Now think about Newton's second law for a second. Normally, when a sound wave hits a material, that material yields. It gets pushed in the direction of the wave, transmitting the sound. But with this highly specific honeycomb and silicone geometry, something wild happens. When a low-frequency sound wave hits it, the silicone plate actually oscillates in the exact opposite direction of the incoming wave. It pushes back. It creates an anti-resonance. The material behaves as if it has negative mass, acting like a solid, unyielding brick wall that just violently rejects the sound.
This comparison really hits the nail on the head when you look at the old tech versus the new. On one hand, you have foam, which passively attempts sound absorption. It just kind of sits there, trying to trap and convert a tiny bit of sound into heat, but it leaves most of that low-frequency drone totally intact. On the other hand, the Metasurface gives us total reflection. By oscillating perfectly out of phase with the noise, it literally pushes back against the sound wave, stopping it dead in its tracks before it can ever reach your cabin.
When you map this out in an analytical model, you can see exactly where this anti-resonance kicks in. For this specific dragon skin silicone design, any sound frequency that drops under 2056 Hz causes that dynamic mass density to plunge below zero, meaning the entire spectrum of annoying low-frequency road noise, the rumble, the hum, the drone, is literally blocked by physics from passing through.
Part 5. Lab tests to highway drives. Theory is great and all, but how does this lightweight honeycomb actually hold up in the real world?
The researchers obviously had to prove this, so they started in the lab. They built a custom static tire cavity rig out of medium-density fiberboard and aluminum sheets to mimic the exact dimensions of a real tire and blasted it with white noise. Once that worked, they took it to the streets. They lined the 15-inch rims of a 2008 Toyota Prius hybrid, first testing it with traditional foam and then swatting it out for their custom acoustic metasurface to measure the real, tangible difference inside a moving car.
Before we look at the results of those tests, keep this exact number in your head: 230 Hz. That is the fundamental cavity resonance frequency of a standard passenger tire. 230 Hz is that exact specific droning pitch that gives you a massive headache on a 3-hour road trip. To be considered a success, any new soundproofing literally has to crush the noise at this specific frequency.
Let's check out the static lab results first. Because the lab rig wasn't a moving vehicle, the fundamental cavity mode peaked slightly lower, around 81.5 Hz. You can see the raw white noise here, and the dashed line showing what happens when you add traditional foam. But look at that red dotted line. That is the acoustic metasurface. Right at the absolute peak of the noise, the Metasurface crushed it by 3 decibels more than the foam did. Now, you might be thinking, 3 decibels? That doesn't sound like a lot. But sound energy is measured logarithmically. A 3 decibel drop literally means the actual physical sound energy in the room was cut entirely in half.
But the highway tests? Those were even more definitive. They took that Toyota Prius out onto newly paved asphalt and ran it anywhere from 20 all the way up to 60 miles per hour. Keep in mind, a Prius runs entirely electric until about 40 miles per hour, when the mechanical engine finally kicks on. But look at the data. Across the board, at every single speed, the Metasurface stayed consistently quieter than the foam. Even when that gas engine turned on and the overall vehicle noise spiked, the Metasurface proved without a doubt that it is vastly superior at blocking tire vibration. Finally, Part 6. A much quieter future. Honestly, we are looking at a fundamental breakthrough in how we handle sound. The main takeaway from all this data is just the sheer, undeniable efficiency of this new tech. By simply using a lightweight, carefully structured honeycomb and a thin layer of silicone, researchers managed a massive 2 to 5 decibel reduction over foam. It is incredibly effective across a huge range of low frequencies under 1000 Hz, offering almost total acoustic reflection. And the coolest part? It is entirely scalable. By just slightly tweaking the thickness of the silicone or the exact size of those honeycomb hexagons, engineers can target completely different frequencies. Which leaves us with a pretty exciting horizon, don't you think? As we wrap up this explainer, I want to leave you with a thought. If we can literally hack the physical properties of mass to create an anti-resonance force field, one that silences the deafening roar of a highway tire at 60 miles an hour, what other annoying noises in your life could a Metasurface finally turn down? Imagine airplanes, massive industrial machinery, or even just the noisy walls in your apartment building, all instantly muted by a paper-thin layer of honeycomb silicone. It's a wildly quiet future to think about. Thanks for joining me on this deep dive, and keep your ears open for what's next.